Hello, today we're looking at this question here. They were looking for an equation of motion for each of the particles and the wedge. So the 1 kilogram, the 5 kilogram and the 8 kilogram wedge. So the first thing we're going to do is just draw out a diagram so we can basically just visualize all the forces and the accelerations on each of the different particles. So we're told of angle A there. We're told tan A is equal to 3 over 4. So I'll draw that out in a second. Then we've got this 5 kilogram mass, which is dangling off at an angle, which is a little more complicated than the usual question, but it's very easy to deal with. And then we've got the 1 kilogram mass getting pulled up by the 5 kilogram mass on the same string. So this 1 kilogram mass has a restorative force, or the normal force pushing against it from the wedge, and it's got its own weight force of 1g. The 5 kilogram force has got the tension force from the string pulling it back up, and the 1 kilogram mass is also affected by the tension because it's on the same string. So the 5 kilogram force is accelerating down with acceleration f at that angle there, and then 1 is accelerating up at the same acceleration because they're attached by the same string, and the whole body is moving to the left with acceleration a. So I've just written up there a diagram of tan A is equal to 3 over 4, so sine A is 3 over 5 and cos A is 4 over 5. So you're able to split up that weight force of the 1 kilogram because the angle right in there, it's very hard to see, sorry, it's quite small, is the same as angle A. So you've the force opposite the or is cos A, which is 4g over 5, and then opposite the angle is sine A, which is 3g over 5. So you just have to split that up to get one parallel to the plane and one perpendicular to the plane. So I'm just going to draw the accelerations affecting the 1 kilogram mass here now. So you've got the regular F, which is from the 5 kilogram mass pulling it, and then you've got the A pulling it backwards from the body moving to the left. So you're able to split that again using the same angle A, and then you've got cos A and cos A times the acceleration A and sine A. So cos A is going to be 4g over 5, that's parallel to the plane, and the 3a over 5 is perpendicular. And then I forgot to draw the angle theta there, but I've just drawn it there now. So the forces acting on the 5 kilogram mass, you've got its own weight force, which will be pulling it down of 5 g's, and then you've got the tension force pulling it back up by the string. That's the tension from the string being attached to the 1 kilogram mass. So you're able to split that vector, or split that force into its vector components, one up and one to the side because it's being pulled up and to the side by t. So you've got that angle in there is going to be the same as theta because of internal or alternate angles. So you've got t cos theta because it's adjacent, and then across from it you've got t sine theta because it is opposite it. So if we draw the accelerations for the 5 kilogram mass, just like we did for the 1 kilogram mass, I've zoomed in here, hopefully it works. We've got A pulling it across, and we've got its own F pulling it down to the right, just from the way it's swinging itself. So you can split that F into two separate forces, one vertical and one horizontal. So you got F cos theta for the adjacent side and F sine theta for the opposite side. So for the 1 kilogram mass, we're asked to find equations for it along the plane and across from the plane. So we've got the sum of forces is equal to mass times acceleration. So if we take up and to the right as our positive direction, because that's the way it's accelerating due to the 5 kilogram mass, we've got t pulling it up that way, and 3g over 5 pulling it backwards. That's going to be negative. So t minus 3g over 5 is equal to mass times acceleration. So you've got its mass is 1 times acceleration. So you've got f pulling it up and 4a over 5 pulling it back. So f is going to be positive, so 1 times f minus 4a over 5, because 4a over 5 is this acceleration opposite that direction. So then we can do the exact same for perpendicular to the plane. where because our acceleration is going up and to the left, and so is or, we'll take or as our positive direction. So we have or for the same sum of forces is equal to mass times acceleration, or minus 4g over 5, because that's going opposite, is equal to mass 1 times acceleration. We just have one acceleration here, which is 3a over 5. So then we do the same for our 5 kilogram mass. We just draw out the forces and we have our accelerations there from earlier. So yeah, just pointing it all out again. So you've got the sum of forces is equal to ma. So if we go for the vertical, you've got for the forces pulling it down is 5g. The force pulling it back up is t cos theta, as we found earlier. And because it's accelerating downwards, you've got mass times acceleration, so 5 times f cos theta. So then we're going to do the exact same for horizontal. You'll notice it's the same thing over and over again, just using different forces and directions. So it's moving to the left, because from tangent force, you've got t sine theta is equal to 5 times a minus f sine theta, because a is also moving to the left, so that's going to be the positive acceleration in this example. So we've got 5a minus f sine theta, because f sine theta is what's pulling it, is the force to the right, and which is negative. So now for the wedge, I'm just drawing out another diagram here just to show just the forces on the wedge. So firstly, it's got the resultant force from the 1 kilogram mass pushing it back in. I've drawn a very small by accident here, but it's the same thing, just inverted. So opposite the angle of A, you've got 3 or over 5, and then adjacent you've got 4 or over 5. Okay, so then we've got the tension force from the 1 kilogram mass pulling it back. So that's going to be the same angle as A for the same alternate angles as before. So adjacent is 4t over 5 and 3t over 5. T is the tension force in the string. And then if we go and draw the tension for the 5 kilogram mass, you've got at the angle theta, you're going to have t cos theta and t sine theta. So sine theta for opposite and cos theta for adjacent. So now the question is only asking us to deal with the horizontal components, but we can draw the vertical ones in. So you've got n, the normal force, and 8g, its own weight force pulling it down, and the whole body is accelerating to the left with acceleration 8. There's only one acceleration, it's not moving up or down. So the force equation for the wedge in the horizontal direction is the same process as we have done thus far. So you got sum of forces is equal to ma. So everything moving in the same direction as your acceleration is positive, everything moving opposite that is negative. So the only force that we have moving pulling it to the left as the acceleration is 4t over 5. Everything negative, we've got 3 or over 5, which is going to the right, and t sine theta, which is going to the right. So we've got minus 3 or over 5 and minus t sine theta, and that's equal to mass times acceleration, which is equal to 8 times a. So now if you wanted to find the same equations for vertical, because it's not moving up or down, the sum of forces up equals sum of forces down. So you've got n is equal to 4 or over 5, because that's going down, plus 3t over 5 plus t cos theta, because those are all going down. Thanks for watching. If that was helpful, I hope it was helpful anyway. If you've got any suggestions or requests, just throw them down below.